Hello everyone, my name is Juan Fraire, and in this presentation I'm going to discuss the expected file delivery time of DTN protocol over asymmetric space Internetworking channel. This work has been developed in cooperation with researchers from the Suzhou University and the Nanjing University of China, the Lamar University of Texas, and the CONICET in Argentina. This presentation actually was given in the Space Terrestrial Internetworking workshop of the IEEE Conference on Wireless and Space and Extreme Environments, WISE, in 2018. So it is well known that the Terrestrial networking architecture has been proposed and also standardized and is on standardization track both on CCSDS and IATF for space and deep space networks. The Terrestrial networking basically is designed to operate over long link delays and disruptions, and the way to do this is basically using store, carry, and forward data transfer, and there is no assumption that an instantaneous response from an immediate neighbor in the network. These networks are also assumed to have very high data loss rate, so channel stability is not assumed in DTN, but in order to accommodate most of space channels. And most importantly, and what we will be focused in this work, is that the channels that we use to operate this network are considered highly asymmetric and sometimes unidirectional channels. This means that the forward channel might be of different data rate than the return channel, if any return channel is ever present. And this is very different from what we used to see in traditional internet protocols such as Wi-Fi or Ethernet or any other protocols which are completely bidirectional, and not only bidirectional but symmetric in terms of data rate, right? So DTN is specifically focused to tackle this type of channels, and this is going to be our focus of research in this presentation. And the bundled protocol is a specific standardized protocol that fits the delayed terrestrial networking architecture. The bundled protocol is designed to operate over convergence layer adapters to run on different underlying protocols. So as we mentioned, asymmetric channels basically assumes that there is a forward channel that may have a different data rate than the return channel. This has basically two implications in a space-to-ground session. One of them is that the ACK channel rate, this is basically the return channel that is bringing us back the acknowledgements of the packets that we sent on the forward channel, is lower than the data channel rate. This is not a problem for small-sized ACK, right? If this imbalance is not so big, this small-sized SDK will basically be occupied less time in the channel than the data that we are sending in the forward channel in this highly imbalanced bidirectional channel. However, when ACK channel rate is much lower than the data channel rate, the asymmetry can degrade the data transmission performance because the ACK time occupation in the channel can be actually bigger than the main data that we are sending in the forward channel. In case we are using the bundle protocol, we will be talking about bundles instead of packets. So the objective of this work is to develop an analytical model for estimating the transmission performance of bundle protocol when used with a reliable delivery service and using a highly asymmetric channel rate. So we can actually study what is the impact of this asymmetry in the bundle protocol. But when bundle protocol is set to configure to use a reliable delivery service, we say that we are using the custody acceptance mechanism that bundle protocol uses for ensuring that the data is delivered reliably to the next node or the next hop in the route. So let's take a look at an example to start understanding how the system model can actually be derived. So this is a possible file transfer between two nodes that's basically uses 5 bundles in order to transfer this file to the destination. So on the first step here on the left, there is these 5 bundles are transmitted, and only bundle 3, and bundle 3 and 5 are lost in the way because of the unreliable channel or channel error rates. This means that custody ACK, the custody acknowledgement from the destination node, is going to be issued only for bundles 1, 2, and 4. These are going to be sent back to the sender node, and we see in this example that actually this custody acceptance for bundle number 2 is also lost in the way, right? So the original node receives acknowledgement 1 and 4, and these are the only bundles that are considered successfully transmitted. After this, the resend timer, the RTO is met. The sender node will be transmitting again all the bundles that are supposed not to have arrived in the first attempt. And these are bundles basically 2, 3, and 5 again. So we see that in this example, bundle 3 is lost again on the way. So then the node is going to issue ACK for bundle 2 and 5 only. And then for the original node, the sender node is going to have bundle number 3 without being sent yet. We'll retry number 3 after this RTO timer is completed, and then it's going to transmit the bundle again, and then this bundle is going to be received successfully, and the ACK is going to be sent back, and so we have 1, 2, and 3 rounds in order to fully deliver this packet in a scenario where the channel asymmetry is not so big. This is the ACK, or the time of the custody acceptance, is smaller than the bundle that we are studying here. We see here that we have at the end of the model what we call TTransLast, which is basically the transmission time involved in the last round, which is basically, as we see here in the model, we have the time of the bundle, and then the time of the retransmission timer, and then time of the bundle again, time of the retransmission timer, then time of the bundle again. Then we have the propagation time of the first bundle, and then we have like an overhead, which is basically whatever extra effort is required to get the last bundle to the final destination. This is what this TTransLast parameter actually measures, and this is what we are going to try to model in this research. But what happens when channel asymmetry is even bigger, which means that the time of the custody acceptance packet is bigger than the bundle packet? And this is what we see here in this scenario, where the same packet loss schedule is applied. So again, the original sender transmit a file with 5 bundles. Basically, this low ACK channel rate delay each round a little bit more the reception of the ACKs, basically, right? So this is basically start to spread away these different timings, and will have a final impact in this TTransLast parameter we mentioned. If we again still measuring this time of the bundle, time of RTO, time of the bundle, time of RTO, and then time of the bundle and time of propagation, this TTransLast parameter in the end is also going to measure the delay of including the time of the channel occupancy of the custody acceptance packet, which is where we're seeing here. This is what we will try to model in order to get an accurate estimation of what's the overall file delivery time in this type of scenarios. So basically, as we mentioned, TTransLast is an accumulation of the time caused by the late arrival of all the custody acceptance. So I'm going to quickly go over the different equations or the different aspects of the model, and we're going to assume that L file is the length of the file, the size of the file, and then we have the size of the bundle and the size of the bundle head. And with these three parameters, we can actually estimate which is the number of bundles that we need to use in order to carry all the data that needs to be delivered with the file. We will denote the MTU unit of the link as LMTU, and also the LIP head of the size of the IP head. And by using these parameters, we combined with the UDP header and also the length of the bundle we have just discussed, we can get the number of frames that are actually required in order to transmit a given bundle, right? So this is the length of the bundle plus the UDP head is divided in all the MTUs, which are also occupying the IP header. We will therefore describe that what's the size of the bundle of an encapsulated bundle is going to be basically the length of the bundle plus the UDP header used for the bundle, and then we will have an extra header, an extra overhead, one for each of the frames, and this will be multiplied by the size of the IP header and the underlying link header. So this is the size of the whole transmitted encapsulated bundle. From this size, we can actually derive what is the time occupation in the channel. So the time of a bundle is obviously the size of this encapsulated bundle, basically encompassing all the overhead of the link layer, of the network layer, of the transport layer, and then the size of the bundle over the data rate of the channel data rate. And same happen for the ACK duration, or the custody acceptance duration, TCA. So it's the length of the TCA plus all the headers involved, and this is divided over the channel data rate of the ACK channel rate. Sorry. We are not assuming the ACK is fractionated or as had happened with the bundle protocol. So now let's assume that we have the tprop as the link propagation time and the RTO timer modeled in TRTO. And we will say that the n round is the number of transmission attempts for delivering the entire file to the destination. So in the example we have just seen, we have essentially two three round times tries, and then we have the last propagation and then the TTransLast to deliver the data for the destination. The total file delivery time is therefore this equation that we have here. It's very simple, and let me just describe this formula with a picture in the next slide. So using the example we have just seen, so we see that the number of rounds we used in this previous example was 3. So 3 minus 1 is 2, and these are the two main rounds attempts, which are basically the time of the bundle plus the time of the retransmission timer. Then we have again a time bundle for the final transmission of the first bundle and the propagation time for that bundle, and then we have this TTransLast parameter that basically models and embraces all the extra time required to deliver the file to the destination. So to estimate the different rounds, we will obviously need to consider the bit error rate of the channel. And the bit error rate of the channel, if this is modeled as a p value, the probability that a bundle is corrupted by a channel is described by this formula here, basically to understand which is the probability that the given bundle is corrupted by the channel noise. So let's also let a random variable used to understand the number of transmissions rounds needed to deliver the ETH bundle, basically. So this random variable will follow a geometric distribution because this is like a continuously growing attempts. So 1, 2, 3, 4, and so on until this variable, the bundle is successfully delivered to the destination. And obviously we are basically caring about which is the maximum attempt of delivering of all this round in order to deliver the complete file. So basically this maximum attempt is going to be the maximum value of all these random variables y, and this the expected variable of this expected of x in this case can be expressed by this formula. We do analyze this formula and prove this formula in the paper, so we refer you to the paper, but we can get a good estimate on an analytic estimate on what is the expected value of this round, basically the number of rounds that it's required to deliver a bundle successfully. This number is then rounded up to an integer, which is we cannot have fraction numbers of rounds in this case. So, and then finally we need to express what this TTransLast time means. Essentially we can basically average what this TTransLast means, and it's essentially the number of bundles that we are requiring to transmit minus 1, because remember that the first bundle is not considered. We have the time bundle in the overall equation, and then we multiply this by the maximum value of the bundle or the custody access times in terms of time duration of the channel. And this is where the asymmetric channel can take a role in the equation, a governing role. So this is whether if the time occupancy of the channel of the custody access time is bigger, then this parameter is going to dominate, this TTransLast parameter, and otherwise the T bundle will do it. And this is where our model actually is able to fit also not only symmetric and asymmetric, but also highly asymmetric channel data rates. So putting all this together, the overall time delivery of the file, here we are replacing this number of rounds of the attempts by the expected value we just seen, and also the TTransLast parameter we have just seen to get this final expression that can actually indicate us what's the overall time needed to deliver a file to the destination. So how do we validate this model and this expression? We did some experiments, and on the SCNT testbed, the NCST stands for Space Communication and Networking testbed, and this is a testbed that is accessible at the Lamar University with Professor Ruhai. His student was actually who executed these experiments. Until we use these specifics of the computing, and we use the Interplanetary Overlay Network software version 3.6 B for executing the experiments for the bundle protocol. These are the specification of the experiments. So we are transferring a 20 megabyte file size over a 10 minutes propagation time, mimicking what would be like a cis-Martian channel. We also have a wide Gaussian noise channel with a emitter of rate of 10 to the minus 6. We are specifying a highly asymmetric data channel rate to ACK channel rate of 300 to 1. So this is a downlink of 2 megabits and an uplink of 6.7 kilobits per second. And we're going to trade and to explore different bundle sizes from 1 kilobyte to 64 kilobytes without fragmentation. We are not fragmenting because we are using UDP conversion layer, and UDP is an underlying layer where the maximum packet size can be 64 kilobytes. And these are the header values that we are using for the model and the length of the custody acceptance size. We are obviously using custody transfer, so because we're basically running over an unreliable channel, and we need custody as an ACK, as a confirmation of the data. The data is being delivered to the destination. And these are basically the experiments results. On the left, we can see the file delivery time for this experiment, and here we can see in blue the model results, and on red the experimental measurements we did. Some effects that are worth highlighting is this what is the slope from as with the bundle size increases, and this is basically how the header is not becoming so much present in the overall throughput that is being used in the channel. The smaller the bundle size, the more significant the header presence and therefore the overhead. And this is continuously decreasing as the bundle size grows higher. However, as the bundle size grows higher, the probability of errors happening at the bundles increases, and this is what makes the number of retransmission efforts to move up, and therefore increasing the delivery time of the data. And since we are running on a 10-minute channel delay, this retransmission of a lost bundle on the way is quite expensive, and therefore this can be seen as these little steps in the delivery time. And we validated that the number of retransmission effort actually matches these steps here on the left, on the right, which basically shows as the bundle size gets bigger, the retransmission times happen more often, and the errors happen more often in a bundle, and they need to be retransmitted. And this is what actually we are validating via the experiments we are doing. So we derive an analytical model to estimate the file delivery time in highly asymmetric channels. The model fits the results obtained from experiments in the testbed, and we actually can say that the bundle protocol and the custody transfer mechanism is effective in handling the effects of asymmetry in channel data rate. So this is all, and basically this concludes my presentation. So thank you very much for your time.